Yeah, I'll cue you in and yeah.
Okay, sounds good, sounds good.
All right, hello Internet, we're live.
Hey everyone, welcome to episode 20 of the Stanford MLSys seminar series. I'm Curran. We have with us today Dan, Piero, Fyodor, and our guest today, Lin Ma from CMU. So as always, we're gonna have a 30-minute presentation by Lin, and then a 30-minute podcast style discussion where you can ask live questions. And during the topic and the talk, you can also continue to ask questions. We'll keep track of those questions and get them across to Lin. So Lin is an expert on databases. He's a PhD student advised by Andy Pavlo at CMU. And he's interested in databases and machine learning and kind of the marriage of those two areas. So his research has been focused on self-driving database systems or automating databases with machine learning. So he'll tell us a lot about that today. And yeah, so Lin, do you want to start screen sharing? We're very excited to have you.
Yeah, definitely. Let me try to share this now.
And also, yeah, I guess a fun fact about you, Lin, that I saw in your bio was that you were voted the most congenial PhD student by the database group for 3 years running. So congratulations on that. And
sure.
Yeah, looking forward to your talk.
Sure. Yeah. Thanks a lot for the great introduction, Karen. Oh, I hope everyone already see my slides.
Yeah, your slides are great.
Okay, cool. Sounds good. Yeah, thanks a lot for the introduction. And like Karen said, my name is Lin Ma. I'm from the CMU database group, and just very excited to be here today at the Stanford MLSys seminar to talking about a new self-driving database that we are building called NoisePage. So first, I want to mention that I noticed many of the talks or previous talks in this avenue focusing on system designs to accelerate machine learning process. But today, my talk is more on the opposite direction, where we're actually applying machine learning to optimize the system performance, right? So this may be a little bit different than the usual content you may hear in this seminar, but I think this topic would actually could give some interesting insight, hopefully, on how machine learning is used to develop a new generation of systems, as well as what will be the challenges, what do we care about in this context, etc., etc. So hopefully there will be something fun from the audience. All right. So let's go. So firstly, I want to mention, or I want to talk about why do we want to even go into this direction of building a self-driving database, right? So database systems have becoming an essential piece for many of the modern applications, especially in this data-driven era. However, they are also becoming more and more complex and becoming pretty difficult to manage. So according to these reports, personnel is already estimated to be almost 50% of the total ownership cost of a database system. And also more than 70% of the DBAs, or database administrators, think that performance tuning occupies most of their time. So this database administration process is not only laborious and costly, but it is also pretty difficult to scale. So according to these same reports, more than 70% of the DBAs are also managing increasing number of databases over the year. And then for large corporations or even cloud vendors, they even need to host thousands or even millions of databases at the same time. So this manual database administration process has really becoming a bigger and bigger impediment for modern data-driven applications. Okay. So of course there are existing solutions, right? So what are them? Well, there are many existing tuning tools developed by vendors and researchers over the years. But the problem is that most of these tools still require extensive human guidance, right? So in a typical scenario to apply those tools, a DBA would first need to prepare a sample workload of the application, right? And then prepare some spare hardware to fork a copy of the database, and then run those tuning tools to get a set of change recommendations, okay? And after that, the DBA will need to examine those recommendations, pick the best one using their domain knowledge or using some testing, and finally decide when to apply that recommendation and apply it manually. And oftentimes, they also need to do this carefully when the workload volume is low, right? Such as 3 a.m. or 4 a.m. in the morning, which is not really a pleasant task. And furthermore, most of these existing tuning tools only focus on a single aspect of the database at a time. such as indexing, partitioning, or knob tuning, which just means that the database administrator has to repeat this onerous tuning process over and over again for each of these aspects of the system. Right? So all this motivate our exploration on a new generation of self-driving database systems. So we define a self-driving database as a database that can configure, tune, and optimize all system aspects holistically without any human intervention. So these aspects would include physical design in database terminology, or in the database context, that would be building some auxiliary data structures such as indexes, or data placement, such as putting data either in hot or cold storage, or tuning the SQL queries themselves, changing some configuration knobs, or even scaling resources up and down. Right? So all of those aspects. However, there are still a few aspects that a database system would need to perform that may fundamentally require human judgment, such as the access list control, right? And the self-driving database may not be able to decide who should have access to what data. So, and then it may not be able to automate those aspects. So we think there are a few reasons that make it possible to build a self-driving database today or right now instead of 20 or 30 years ago. So the first is that in this data-driven era, not only the database system can store more data, but also it can collect more metrics and store more stats about the system states, right? So that the system can extract knowledge and patterns out of those data to help the system to optimize itself. And the second is that the improvements in hardware technologies allow us, again, not only to store more data, but also to process those data much faster and then retrieve information, doing calculation, and then perform the self-driving operations much more efficient. And lastly, there are also recent advances in AI or machine learning that help provide more convenient tools and better algorithms to achieve the self-driving goal. And I'm pretty sure many of those audience today, or even of some of the panels right in the Zoom call, very well aware of the recent development of those things. All right. So let me just introduce the self-driving architecture that we are developing. But before I get into the details of self-driving databases, I actually want to first make an analogy to self-driving cars. So I should clarify that I'm just going to explain a very simplified view of self-driving vehicles. In actuality, they are much more complex. And I feel like maybe many of the audience today are more familiar with self-driving cars than myself, but still, I think it would be a good analogy for our understanding purposes today. All right. So again, on a very simplified view, a self-driving car would first need a perception component, right? That uses its cameras and radars on the vehicle to observe other vehicles and pedestrians on the road, as well as predict where those things are moving to, right? And second, a self-driving car has models about the effects of its potential actions. I think in that terminology is called mobility models. And for example, if you turn the steering wheel by 20 degrees or hit the brake, what will be the effect, right? What will happen? And for cars, usually these are physical or mechanical models, I mean, already there when you build a car. But for databases, it's a little bit different. I'll get into details. So. And lastly, there would be a planning component, right, that uses the route perception as well as the models to estimate the effect of different actions to plan a sequence of actions to get to where the car wants to go. So our design of a self-driving database actually shares analogies to the self-driving car architecture that I just discussed. So our architecture for self-driving database first contains a workload forecasting component that observe and predict what the workload that the database is going to execute in the future. Because you need to know what you are going to optimize for, so that you optimize for it. And second, there's a behavior modeling component that builds behavior models to predict the cost and benefit for different self-driving actions, such as building indexes or changing some configuration knobs in the database system. What will be the effect of those things? Right? And lastly, an action planning component would plan actions to optimize the system performance given the forecasted workload and the estimated action behavior. So in this talk, I will first briefly discuss one of our previous work on a workload forecasting framework for self-driving databases. And then I will spend most of the time on a framework we just built and published to generate database behavior models. And assuming if we still have time, I will introduce at a very high level our ongoing work to build the last planning component. As well as, again, if we have time, I'll also mention how we are integrating all those components into the new self-driving database that we are building called NoisePage. All right. So let me start with the first component. So we contend that the first step towards building a self-driving database is the ability to observe and predict the workload in the future. So this is pretty important because certain actions that a self-driving database needs to apply, such as building indexes, partitioning the data, or scaling resources, may take a long time to finish. For example, building an index to accelerate some queries may even take hours, right, for a table with billions of rows. So it might be too late that you only apply those actions after you observe that the workload already requires them. And furthermore, you may also want to apply expensive actions when the workload volume is low to avoid resource contention. So we define the workload forecasting problem for self-driving databases as the ability to predict when, how many, and what queries will arrive to the database system at a given future time point. So beyond this, there are also two important concepts. The first is that how long into the future that we are predicting, such as 1 hour or 1 week from now, right? That's what we call prediction horizon. The second is what is the granularity for such prediction, such as per minute or per hour. That's what we call a prediction interval. So a good workload forecasting framework will first obviously achieve good prediction accuracy for different combinations of horizons and intervals. And then it also needs to capture the major database workload patterns, which I'll give some examples. And lastly, it should achieve good balance between cost and accuracy. So there are a few challenges to achieve this task. The first is that in order to apply a self-driving database in production, the workload forecasting needs to capture and predict the workload patterns online and also handles the changes in the workload patterns dynamically. And second is that modern database workloads can have high volumes. So for the purpose of this project, we collected query traces for 3 medium-sized real-world workload database workloads, and all of them execute at least millions of queries per day. Right? And then last, there can also be different patterns in database workloads. So for example, in the first query trace or workload trace we collected, which is from a Pittsburgh bus tracking service, there's a diurnal workload pattern that follows the human living cycle. Essentially, there are more queries during the weekday and on daytime compared to weekends or night. And then in the second trace, which is from the CMU application and admission website, there's a different growth and spike pattern with a peak around the admission deadline. So not only different database applications may have those different patterns, but also different subsets of queries within a single workload may also have different patterns simultaneously. Right? So a good workload forecasting framework needs to capture all those patterns. To address those challenges, we developed a framework called QueryBot 5000 to build the workload forecasting component for self-driving databases. So at a high level, it works this way. When the application sends SQL queries to the database forwards the queries to QueryBot 5000. And then these are all historical queries that arrive in large volume. Okay? Then these queries will go through the 3 steps of QueryBot 5000, namely pre-processing, clustering, and forecasting, which I will briefly talk about very soon. And after these steps, QueryBot 5000 generates compact predictions for the future SQL workloads used by the later self-driving components. Okay, let me just go over those 3 steps now. So first, as I mentioned before, there can be millions of queries arrive to a database system per day, even for just medium-sized applications. So it will be too costly to capture the patterns for all of those queries and then build forecasting models for each single one of them. There has to be some compression. So the first thing we did is to leverage the structural pattern of database queries, which are usually written in SQL, actually just in short of structured query language. So what we did here is that we are going to extract the constant parameters out of those SQL queries and only record the patterns and build forecasting models at those query template level. And of course, the distribution of those parameters would matter. So we keep certain parameter samples for each query template using a reservoir sampling. Additionally, we also group semantically equivalent queries to the same template. So this simple step allow us to reduce the millions of queries that we need to forecast per day to thousands of query templates. So this is good, right? But even with the last step, it's still too costly to build forecasting models for thousands of query templates, especially if you want to use some advanced machine learning techniques such as neural networks. Right? So next, we have a clustering step to further group similar query templates together. So for clustering, probably the most important question that we care about is just what is the similarity metric that we are going to use. So there are a few canonical options. For example, the first would be physical features, which are the runtime metrics that the system can record after the query is executed, right? Such as how many tuples read. But the problem with those physical metrics is that they may actually change when the self-driving database applies certain actions, such as building an index, then the queries are reading less tuples. So the clustering result would become invalid, and this is not good. Then another canonical option is logical feature, which are the information you can extract from the query logical composition, such as what the type of the query, how many columns, references, etc. In other words, from the abstract syntax tree. So this is certainly independent of the self-driving actions. But unfortunately, in experiments, we found that there's not enough information in those logical features to generate a good clustering results. So now, what we eventually end up using is what we call the arrival rate feature or temporal features. So our observation is that if we are generating models to predict the query arrival rate in the future, then why not we just directly group query templates based on their arrival rate pattern, right? And then we only need to build one model for each arrival rate pattern. So the reason we can do this in database context is that for many database applications, queries are generated often in batches using tools like ORM or stored procedures. So many subsets of queries may arrive at the database system at a similar time, and thus may have similar arrival rate patterns. So to illustrate this, assuming this is the arrival rate history for a single query template, we're just going to sample certain arrival rate values at a few timestamps to form the arrival rate feature, and then do the clustering based on that. So we found this pretty effective. And in fact, if we only consider the largest file clusters based on this arrival rate feature, then that already covers more than 95% of the total workload volume of all our 3 medium-sized real-world applications. And then we only need to build forecasting models with these largest clusters that can already cover the majority of the workload, which significantly reduces the overhead. Right? Then lastly, to build a forecasting model for each query template cluster, we investigated a number of popular time series forecasting methods with various properties, such as whether they are linear, whether they retain memory, or whether they use kernel methods. And in summary, what we eventually found is that there's no single method performs the best in all of those scenarios to capture all of those different workload patterns. So I guess, again, this audience probably be familiar. In machine learning, one approach to address this is called ensemble, where we just combine multiple models with different properties together to acquire a better predictive power. So in this case, we combine linear regression, recurrent neural network, and kernel regression together, since this gives us the best empirical performance. Of course, there are some other tricks that we apply to improve the prediction accuracy, such as, obviously, you want to normalize your data, normalize the input features. And then we found that predicting the arrival rates of all the clusters together also improves the accuracy, because the model can leverage the relationship between different arrival rate patterns to generate better prediction of the arrival rates. So now I just want to show you one example of the prediction results, which is to predict the query arrival rates for the bus tracking application I mentioned earlier. So I want to clarify that for demonstration, I'm only showing the forecasting for the total workload, but our framework is actually predicting the arrival rates for each individual query template, right? So I'm showing you the results for 2 different prediction horizons. On the top is to predict the workload 1 hour from now, and then on the bottom is to predict the workload 1 week from now. So from this, we can first tell that predicting the workload 1 hour from now is certainly easier than predicting the future 1 week from now. This is actually not bad for a self-driving database, because the system does need to prioritize the optimizations to the workloads in the near future, right? And then for the workloads far ahead of time, there's always the opportunity to optimize them later. And second, no matter for the 1 hour or 1 week horizon, we can see that the forecasting framework both generates reasonably accurate predictions. So now, if you remember the self-driving architecture that I mentioned earlier, I just described our framework to build the first forecasting component, and we think this forecasting ability provides the premises for the later modeling and planning components to complete the self-driving build. And next, I'm just going to talk about a work we recently did to build behavior models for self-driving database. So the task of behavior modeling is to generate behavior models that predict the cost and benefit for self-driving actions, right? Simply put. So to be slightly more specific, the input of those models would be the forecasted workload in the future and some candidate actions that a self-driving database may apply. Okay? And the output would be the cost-benefit estimations for that action on that specific workload. So this could include how long this action takes, how this action may help improve some query latency of the database system, as well as the changes in resource consumptions. So to further explain this a little bit, what we are doing, here I'm showing you an example experiment where we remove an important secondary index from the famous TVCC workload that is used in many database evaluations. And then we are going to create this index back as a self-driving action, but with 2 different choices of actions, right, that would use different number of threads. So we start this workload with no secondary index. As you can see, the query latency is relatively high here, which is bad. Then we are going to apply the create index action at around 50 seconds. We can see that right after the action start, the queries actually become slower because the index creation is competing resources with the regular database queries. And then using 8 create index threads would cause the queries to be even more slower than 4 create index threads because more resource consumption. But then the index creation finishes much faster with more threads, so the queries become faster earlier. So we think the ability to accurately predict the effects of those actions is really the foundation for a robust and effective control of self-driving databases. But again, there are a few challenges, right? The first is that the database system is a pretty complex software. So if we want, for example, to use a single monolithic machine learning model to capture all aspects of the system, including all types of workloads and all the possible actions, the models can be very high dimensional. And also, subsequently, this may require lots of training data to train and may be difficult to debug. And secondly, in the multi-core environments, actions and queries can also run concurrently. So the models would also need to capture all kinds of interference between concurrent operations, which can further increase the number of possible inputs exponentially. And furthermore, there are, of course, some previous works on database modeling, but then there's actually, most of those work are focusing on the modeling algorithm, but there's a lack of a principled framework to generate the appropriate and sufficient training data to train these models. Especially for certain database operations, it can also be very expensive to collect training data, right? For example, if you want to know how much time it will take to create a secondary index for a table with 10 billion rows, well, getting that single label for that single action may already take hours. And lastly, for the practical application of self-driving databases, those models should also have a good interpretability, debuggability, and adaptability. So to address this challenge, we present an offline framework that generates behavior models for self-driving databases called ModelBot 2. Let me just give a high-level overview of the MB2 process. So MB2 will first uses a set of specialized runners that fully exercise different components of a database system. And these runners would use the same lightweight matrix collection system to collect the training data, and then send to a programmatic training framework that would use this data to generate 2 types of behavior models for the database system, namely one set of operating unit models, and then another separate interference model. And then now I'm going into a little bit of details now. So the core idea of MB2 is to decompose the complex database functionality into small and independent, in our world, operating units or OUs to model them separately. Okay? So the main benefit of this is that each model would be relatively low dimensional, does not require a huge amount of training data to train, and also are friendly to interpret and debug. And in this case, it's also easier to adapt those models under software update. Because when that happens, we only need to change the models for the specific OUs affected by a software update, but not everything. So to give you an example, we decompose our NoisePage system to around 20 operating units, including typical database operations such as building hash tables or creating indexes, etc. And then for all of those OUs, they can have different input features, right, depending on what kind of operation that the OUs may do. And these features may also include the database configuration knobs that may impact the corresponding OU's behavior. So for example, our OU model for serializing the log record at the bottom of these examples may just include the log serialization interval, which is the configuration knob that would affect the behavior of that OU. Then all of those OUs would share the same set of output labels, which would include the OU completion time, as well as different resource metrics, such as CPU, I/O, and memory. And note that for one type of resource, there may also be multiple fields in the output. For example, the CPU metrics can have a CPU time, cache references, cache misses, etc. And then during the inference time, the self-driving database will just sums up the prediction for all the OUs to estimate the behavior of the entire system. So to collect training data for those OU models, we use a set of specialized runners that we wrote ourselves that exercise each OU through some CQ-based synthetic benchmark. So as I'm going to illustrate here, each operating unit or OU is going to be paired with an OU runner to enumerate the various possible inputs for that OU. For example, in this case, the OU runner for the hash table creation OU would just use a set of customer workloads to exercise the hash table creation process with a different number of rows, different number of columns in the table, different kinetics in the table, etc., right, to get the labels for that OU. And then we use a decentralized metric system, leveraging a thread local storage to collect those features and labels with low overhead. And after that, we're going to send that to a robust training framework to searches over a wide range of canonical and state-of-the-art machine learning algorithms to find the best machine learning model for each OU, essentially just using cross-validation. And just note that we found in our experiment, for the scale of our OU and the amount of training data we have, gradient boosting machine performs the best in most cases. But the most important thing I want to emphasize here is that these models are actually workload and dataset independent, which means that they are generic models that we only trained once offline, and then the self-driving database can apply them online or in production to any dataset or workload. Right? So just mentioning another important trick that we developed, which is to address a problem that it could be expensive to collect labels for certain database operations. Right? So for example, building hash table, sort, or create index may need to process billions of rows. So to address this, we leverage one observation inspired by a previous work on query execution modeling, which is that for many database operations, they just have known complexity based on the number of processed tuples. So essentially, if we fix, for example, in this case, sorting a batch of data would just have a complexity of n log n when n is the number of tuples, right? So what we can do is that if we fix all the other input features, but this tuple number, and then if we divide the output labels for those OUs by their corresponding complexity, then we get sort of a per tuple output label that will eventually converge to a constant when the number of tuples gets large enough, right? Because that's the asymptotic complexity. So we only need to collect labels for the OUs with a number of tuples up to that convergence point, which we found is usually below 1 million based on our experiments for our system. So with this approach, it takes roughly 10 hours to collect all the training data that would exercise all the different OUs for our NoisePage system, which we think is an acceptable overhead. And with those models, we can accurately predict the system behavior, such as the latency of queries and the impact of self-driving actions. And we also have experiments in the paper to show that these models perform significantly better than the previous state-of-the-art models, especially on the data sets that have not seen in the training data. So let me skip that slide. And then I just want to mention that another important challenge in this problem is that in actuality, database system would often run in multi-core environments, right? So even though we can decompose the big system into separate isolated OUs and model the OUs separately, but then if different OUs are running together in a multi-core environment, then they may compete for resources. So they may interfere with the behavior of each other. So we also need to take into account of that. Otherwise, the prediction may be way off. So to address this problem, we just introduced another interference model that captures the concurrent impact. And what the interference model leverages is exactly the resource consumption labels predicted by the earlier OU models. So to be specific, the input features of this interference model are some summary statistics of the earlier OU model outputs for the concurrent OUs forecasted to run in the same interval, such as their sum, their mean, their variance, etc. And the output labels would just be the adjustment ratios between the actual OU metrics as well as the OU model prediction due to the concurrent interference. So similar to the OU runners, we also devise a set of concurrent runners that will exercise various kinds of interference among OUs. Right? So finally, let me just go back. Let me just talk about an end-to-end self-driving experiment that we did to evaluate the ability of our models that can estimate the changes in the query latency or the performance of the system when the system is trying to apply a certain self-driving actions. So for this, we just simulate a very typical daily transactional and analytical workload cycle using the famous TBCC and TBCH workload. And just to clarify, we shortened the entire workload duration to 2 minutes to accelerate our evaluation. And in actuality, this daily pattern, of course, would be much longer, right? And in this case, we also assume a accurate workload forecasting per 10 seconds forecasting interval so that we can separate the error of our behavior models versus the error of the forecasting. And lastly, since we are still working on the planner, we don't have a planner yet, we're just going to use an Oracle planner that would pick a configuration knob to change our configuration knob to optimize for the TBCH workload, as well as build an index to optimize for the TBCC workload. Right? So here are the results. And again, in this case, we are primarily looking at MB2's ability to estimate the changes in the query latency so that, given a certain candidate self-driving actions, and because those information were very important for the self-driving database to choose the appropriate actions. So in this, as the result shows, we will first start the TBCC workload and then followed by the TBCH workload. And we can see that, again, during the beginning of the workload execution, the query latency are relatively high because the system are in a sub-optimal configuration. Then this Oracle planner just decides to change an execution knob for the TBCH workload to improve the TBCH query latency. And we can see that MB2 accurately predicts such improvement. And later on, the Oracle planner builds an index for TBCC workload with 8 threads. And again, MB2 successfully predicts that the query latency becomes worse while the index is being built, but then becomes much better when the index creation finishes. And not only that, but also our decompose framework provides detailed insights on the prediction, such as how long this action will take, how much resources that the action need, and even which queries are improved or impacted by the action. And we believe all of this information is the foundation for self-driving database to choose appropriate actions automatically. Since we are already a little bit over time, I'm just going to, at a very, very high level, talk about what we are doing recently on the last component. Maybe just use 1 or 2 minutes to summarize them. All right. So, for now, we are going to call this last component that plans actions for self-driving database, the pilot of the database, right? The goal of the pilot is just to choose the best self-driving actions with the forecasted workload and the behavioral model estimation as the input. And then users of the self-driving database will actually need to specify the self-driving objective. For example, this can be minimizing the average query latency in the database system, or minimizing the 99th percentile query latency. This is actually similar to a self-driving car that you will need to tell the car where you want to go, right? The car doesn't know where you really want to go. Similarly, users will need to specify the objective. And there are some detailed responsibilities, but I will just skip today. But essentially, I just want to mention that the framework that we are trying to leverage to achieve this, to build this pilot, is a canonical framework in control theory called receding horizon control. Right, we are just going to look ahead into a few future horizons, and then planning actions for each of these future horizons. And then you just to pick the best sequence of actions to apply. And to achieve this, we are also actually investigating the planning method that has some recent success, especially in some AI systems such as AlphaGo to play the Go game, called the multi-color tree search, to make this planning process much more efficiently and generate good planning results in reasonable amount of time. Right, so let me just skip this integration slides today. And lastly, I just want to mention a few takeaways for today's talk. So essentially, we talk about that today database administration is really becoming a more and more challenge, especially for many modern data-driven applications, right? And then we are trying to build a new generation of self-driving databases that would address this challenge by automating all those administrative tasks, just except for the ones that fundamentally require human judgment. And we believe that our forecasting, modeling, and planning architecture is the correct approach to build such a self-driving database. And we also talk about the templatization and clustering-based forecasting framework, as well as a decomposed behavior modeling framework to achieve this task. Lastly, I just want to mention that with a self-driving database, there may actually be opportunities to support even a more fine-grained automation beyond what humans are doing today, right? For example, today it would be too tedious and costly for a human to tune and configure knobs for every single query that the system is going to execute. But then for a self-driving database, it may be possible to make a control decision every second, right? To even optimize every single query in fine granularity. So I think there's actually, there will be a lot of interesting and exciting opportunities that self-driving database can enable to make system much more efficient than what they are today. Just want to mention that our system NoisePage is an open source system. So if you're interested, you could check it out or even maybe join our journey. And that's all I have today. And thanks for listening. I'm happy to chat, get any feedbacks or answer any questions. Thank you.
Thank you so much, Lin. Awesome. Could you also, sorry, stop sharing if possible?
Sure.
Thank you so much. Yeah, great talk. And yeah, I just want to remind folks in the audience that you can post your questions in chat and we'll get those across to Lin. Yeah, just to kick us off, I guess, yeah, I'm curious about the analogy you drew to self-driving cars. And I guess I did like, I spent a couple of years doing RL research, so maybe, you know, I see RL everywhere, but like, I'm wondering, like you drew these kind of analogies to learning the behavior model and planning and all of these things. So it seems like there's like maybe standard analogs to these things in sequential decision making. So learning a reward model, learning a model of the world, and then you know, learning a policy basically. So I'm wondering if you've thought about exploring some of those connections a bit more. So just as an example, like I think like the process you described is essentially learning a model and then planning with respect to that. And I'm wondering if you've thought about things like model-free analogs where you directly learn the policy as an example. And just, I think there was a lot of places where I was like, okay, I see how this is like the database kind of version of this problem. So just curious if you've thought about that.
Yeah, definitely. Yeah, I think that's actually a great question to get us started, right? So of course, that's the aspect that we will talk about. Actually, we talk about a lot. We looked into that direction, not really implement the framework that way, but looked into that direction, had discussions for quite some time. And well, of course, I also have some discussions with some of the machine learning professors at CMUs as well, right? So I would say that direction, in your word, the model-free kind of policy learning direction is definitely an interesting and valid alternative. Right? It's essentially it's a different methodology, if you will. Right? So, but what we see in the challenge for that direction in our context would be that a few of them, right? The first is the data efficiency, right? So first of all, I mean, those like model-free methods are not well known for, I mean, efficient on have small number of training data, right? You may need lots of them, and the database system is a pretty complex software. So if we do that, I mean, when the dimensionality is high, you need more data. And also in that case, as I mentioned in my talk, collecting training data for some database operations is expensive, such as building index. One label will take hours. Then another aspect is adaptivity, which is that if you train a model offline, right, in-house, and then if you apply on a production workload, well, it's different data set, it's different queries. I mean, it shares some analogy, but essentially it's a different workload, right? Then how well the models may perform in that scenario. And again, also lastly, for practitioners, it's also very good to have interpretability, right? If the users complains about a problem, I mean, if you build the wrong index, why you did that, I mean, what happened, and how you're going to fix that, right? So because of those concerns, in the foreseeable future, we think this kind of a modularized approach is probably a more plausible. But you know, there are lots of research.
Yeah, that's great. Great answer. Yeah, I think definitely I agree with that.
But I would just say there are lots of research on the model-free like approach. I mean, as those improve, I would definitely be interested to see whether there's some method that would be more suitable in our context. It would be an interesting direction. Yeah.
Lin, I really enjoyed the talk. Thank you very much. It was like a really different perspective from most of the talks that we had so far, and that's why it was like really particularly interesting for me. I have a couple of questions. One is more specific and one is more generic. Let me start with the most specific one. I wanted to get an understanding on how those actions in the behavioral model look like, because when you were first talking about them, I started to think about, oh, but are those actions atomic? Are those like, do they have parameters themselves, or are they like sequences of actions? Then when you were talking about the planning, I realized that probably you were talking about atomic actions because the sequence part comes in the planning part. But also, in particular, I was curious about how those actions look like. Like, do I have to, does also the time dimension make sense for them?
Yeah, thanks. Yeah, that's the part I did not get too much time to get to today, right? The planning part, and thanks for bringing that up. So, but I would say the actions has various forms, right? There are many different forms of a self-driving actions or administrative tasks, right, that may be performed in a database system. So there's one big category would be a change in configuration knobs, right? So those things, I mean, such as what is the log serialization interval, right? What is the maximum amount of memory buffer you are going to allow for each query, right? Things like that. And those things would just be a scalar value. That those things would just be atomic, right? You change it, it's done, right? So this is one type of action. The other type of actions would be more expensive ones, right? And often take some time and even has parameters on themselves. One example of them would be creating indexes, right? Which essentially you build data structures like a B tree or hash table to accelerate the execution of certain queries. So for those, I mean, it varies depending on the size of table. It may take from seconds to minutes to even hours. And themselves, exactly like you said, may even have parameters, right, such as how many threads you're going to use and what will be the final limit you're going to allow for the BW tree, right? So yeah, those actions may even have parameters in themselves. But the good thing with the decompose framework is that we also decompose actions into OUs as well, right? It's the same thing. So those OUs for that action may also have corresponding knobs embedded in their input feature, just impact the behavior of that action.
Got it. This makes a lot of sense. Thank you very much for the clarification. And then the second question that I had, which is more generic, is about, working on machine learning. This is like a topic that always comes up, is generalization. So I'm curious of how you're thinking about, so my understanding is that when you collect data, that data is coming from one database. I may be wrong about it, but I'm curious, how are you thinking about in the future generalizing to maybe the same database with different data, or maybe the same dataset with different schema, and so by consequence different queries, or maybe even different datasets, different databases altogether? Is there like a path towards getting to a point where you have maybe a meta model that is capable of optimizing any database?
Yeah, definitely. So I probably need a little bit of clarification, probably because I did not explain this clear enough in my talk. So there are two types of models, right? I talk about today. One type is the forecasting model. The other type is behavior models, right? So the forecasting model is per database, but it doesn't really make that much sense to build a generic forecasting model for different databases with different patterns anyway, because these are arrival rates, right? It's 3 time series. So that is per database, and we need to retrain that for every single one. But for the behavior models, those are actually shared. So the reason we can do that is because first we decompose database into small operating units, right? And then we load benchmarks with a different number of tables, different queries that would fully exercise different possible inputs for each OU. So we have to write a little benchmark for each OU we have, and then exercise different input. So for example, for the OU for creating a hash table, we would have different tables with different number of tuples, different sizes, different columns, etc. Right? But those is indeed an interesting aspect because those runners we wrote ourselves that we think are coverage a decent amount of the input space, but at the end of the day, it's an estimation anyway, right? I mean, it's just impossible to cover the entire space, right? So we as developers, based on our understanding and domain knowledge, we wrote, runners that can generate, we think, sufficient training data which with a small view, and then we apply on any data set. But of course, like you said, if you apply the system online, the workload data set will still be different, right? There'll be cases that you didn't cover yet. In that case, I think it would be very interesting to combine some of the data you can get online with your workloads with the data we have offline, and maybe even improve the model generalization, especially in some special corner.
Got it. That's super interesting. Yeah, thank you very much.
Yeah.
Hey, Lin, I found the analogy to self-driving cars really interesting. I think one of the things that they think about a lot in the autonomous vehicles community is kind of adapting to unseen behaviors. So like in self-driving cars, it's like, weird stop signs or like weird things that you didn't see before. I think we also had a question in the audience about something similar, like seeing kind of workloads change over time and thinking about like how your models adapt to those static things. So I'm kind of wondering in general, how have you thought about kind of the long tail problem and kind of how those things can change? What does that kind of look like in databases? And how have you guys been thinking about it in NoisePage?
Yeah, exactly. That's a great point. So, well, first of all, we haven't done much investigation ourselves on that direction yet, right? Because there are steps, right? We have to build a framework first, and then look at the end-to-end spectrum and see which problem is more important and less important, etc. But that said, we definitely have thought about that. And that's definitely something that occurs to us while we are doing our journey, right? So there are two aspects of this, right? The first is that when there are two possible, the long tail problem definitely exists, right? So that's the first clarification. In the database, there could be, when you, again, using the index example, right? If you are creating an index on a specific column combination with some types, bar chart, followed whatever you never seen in your training data before, then your estimation for the effect of that index may be off, right? So in that case, the model is inaccurate. There will be a long tail problem. And when that happens, there are I think there are two possible approaches to this. The first would be to passively improve that. What I mean is that just have the database running in production with an offline model, but then every time when the database sees some queries, right, and some actions that has an impact of behavior that doesn't really match the estimation of the query, right? Then in that case, we can just collect that training data, incorporate that to our training data set, and then we have enough data, we just retrain the model, right, to improve it, adapt it online using passively, I would call it, collected training data. The other approach, the alternative, actually I explore that a little bit in a different context, but in the context of using machine learning to optimize some of the Microsoft SQL, it's called Azure SQL Server, right? In their Azure cloud, that is to leverage active learning, right? So that we may be able to actively collect additional training data on the copies or replicas that the database may have in a data center or even in a cloud, right? Because in that case, it's easy to fork a copy or replica to exercise some things on that space. And in this case, we can even leverage some metrics like uncertainty estimation, right? If we are trying to apply certain action to a database, but I can look at my model, what's your confidence, right? If the confidence is not good enough, I maybe apply that action on a replica and then see whether it's good or bad. Is the prediction very bad? Again, we need more data and then retrain the model. If the prediction is good, well, maybe it's fine this time, right? So there are different aspects, either passively or actively. But of course, addressing the long tail and maybe incorporate some data online would be very important.
Yeah, thanks. Yeah, that's really interesting how kind of, the similar ideas and tools in machine learning can be applied in kind of interesting ways. I wanted to call out to just two other audience questions real quick about kind of, I guess, extra features in NoisePage. So Johan Hauswald was wondering, have you thought at all about redundancy planning or fault tolerance planning? I think you mentioned something briefly about like kind of duplicates there. And there was another question, any work with any learned indices or anything like that?
Oh, okay. Well, let me, thanks for the question. Let me just answer the second question first, because the short answer is just no, right? So the learning index is not what we do, is not part of our focus, right? Essentially, the line of the learned components work is to use machine learning to make individual components more intelligent, if you will, right? But our work is focusing on using machine learning to automate the administrative aspects of the system to reduce the ownership cost, right? So yeah, they are both using machine learning, but that's not what we do essentially, right? So back to the first question. Oh yes, so for the redundancy planning, so it's a little bit similar to the replica or the active learning idea I mentioned earlier, right? So we have a student that in our group that is currently looking into that direction, right? Essentially, because database systems in practice are often deployed with replicas, right? So replicas, if there's no database downtime, replica may just used as a backup, right? And sometimes it will serve read queries, some read-only queries as well. So again, like I mentioned earlier, if we are not certain about a particular action, or in other case, maybe we are certain, but then the consequence of that action is just high, right? It may have some major impact on the system. Then we can apply some actions on the replicas and see how it goes before we apply it on the primary. So that's definitely possible. But it's still not something that we have thoroughly investigated yet, but it's definitely an interesting direction.
Thanks. Hey, Lin, I wanted to go back to your motivation, which is how much time is spent administering databases. So what do you see as the new role for a DBA in a self-driven DB system? Right, like it opens up a lot of free time for DBAs. Maybe we need less of them, but maybe it opens also some new opportunities, things for them to do.
Yeah. So yeah, that's a great question. So the way I think about this is, okay, so the way I think about this problem is probably from a little bit different perspective, right? So the way I think about this problem is that in this new era of intelligent software, maybe not restricted to database, right? Intelligent whatever software, what will be the role of a human, I know you call it an administrator, human engineer, or a human whatever, right? What will be the relationship between a human and the intelligent system, right? Because previously you could say people need to, at least in database system, people need to babysit the system, if you will. Right? They need to look at how the system performs, whether there's any bugs, when do I create an index? Maybe I need to get out at 4 a.m. in the morning to create an index, I mean, when there's no users accessing it, right? I think in the new era, I don't really feel like human would be completely gone, because like I said, there are certain aspects of the system that would fundamentally require human judgment, right? Such as access list control or security, or maybe which type of the workload we need to prioritize or less prioritize. Right? Those are probably some external information that's just only human can provide, and we need a human judgment. Right? So that's one part of the role that human will need to do. But also the second part is that in this case, I think it's probably not anymore that human need to babysit the software, right? The software itself can make decisions, right? It can have intelligence, right? It can apply things on its own. So in this case, maybe the relationship between a software and a human would be they maybe just be intelligent and independent co-workers, right? They maybe even can be able to work together. And if the software is not doing well, make some mistake, maybe humans can come along and then, I don't know, discuss with the software, if we will, in some form, right? And even come up with a solution together. Right? So I think it would be a very interesting question about what would be the relationship between a human and intelligent software in the future, and what's the HCI aspect of it, right? How do you communicate between them? I think it's all interesting questions to look at in the future. That is how I look about it.
Yeah, no, that's a great point. I was definitely curious, but specifically when it comes to database systems, because this is, really the first time I'm hearing about them, potentially automating away the DBA role. Certainly sounds like there's lots of opportunities there for database administrators kind of role to be redefined in this context.
Yeah, definitely. Yeah.
Awesome. Yeah, so we're approximately 4 minutes out from 2 o'clock. So I just want to get the last audience question in here from Sanjeev, which was around, does your work, I think his question was, can it work on any relational database? Can NoisePage work on any relational database? And does it rely on any proprietary capabilities or any non-standard capabilities?
Okay, that's also a great question. So I'm not sure I can say any, right? That's a very strong claim, right? Can work on anywhere. But I would say, I don't think our framework is very specific. Okay, so NoisePage is a particular database system, right? It's a specific system. But the framework we are proposing is I think it's a relatively general self-driving architecture, right? That can be combined with other systems. At least so far for the workload forecasting framework, that's not has too much it's called a reliance, if you will, on the specific system implementation, right? Because that's just predicting the future rivalries of queries and doing temporization of SQL strings, right? So that I think can be plugged into other systems. For the behavior modeling, well, the most important idea or philosophy we leverage is the decomposition philosophy, right? And then there's no reason you cannot decompose other systems into small operating units to model them and build behavior models as well. But I would actually say that the difficulty of this process to decompose the system into small models and then model them separately would actually depend on how modularized the system architecture is, as well as how familiar the developers are and comfortable with doing this like a cutover of the system, right? So that difficulty may depend, and that is hard to say. But in general, I think the framework can be applied, at least the philosophy and ideas can be applied to other systems as well. Yeah.
Awesome. Dan, go ahead.
Lin, I wanted to ask kind of one last question, a little bit more out there. I think this, using ML for like other fields where in computer science, where people probably didn't think of them initially is really interesting. I wonder, do you have any thoughts on, what's the next self-driving system out there? Is there going to be a self-driving graphics interface, a self-driving operating system, self-driving web browsers? What do you think? Where do you think there's more opportunity to get self-driving software?
Yeah. Thanks a lot for the question. But this question, honestly, I wish I would know that answer as well. I also need to know where I will also be able to know where the opportunities are. But I would just say a general way to look at this, at least I can think of right now, would be instead of seeing where would be the place, we can plug in machine learning, tool, instead of thinking of that way, maybe it makes sense to think about what would be an area or systems that would have lots of ownership overhead, right? What would be the area that would still require quite some human guidance, right? Lots of babysitting, right? And lots of like a human involvement, right? Tedious task, right? If there are certain areas like that, I'm specialized in databases. I'm not that familiar with many other areas, but there may be, right? And if there are that case, and then we can look back to see what would be the best approach that we as computer science may help them. And then during that process, I'm pretty sure there will be certain roles of machine learning, like learned approach, etc. But at the end of the day, I think it boils down to what would be the area that would have a significant value, and it makes sense to use computer science skills to automate them, including machine learning techniques. Right?
Yeah, it sounds like any system which has lots of knobs and a lot of time spent twiddling on those knobs would be ripe for something like a self-driving.
Yeah.
Awesome. Yeah, thanks so much, Lin, for joining us. Since we are just at the end of the hour. Yeah, thank you for your talk, and really enjoyed hearing your thoughts on this area. I want to thank the audience and folks who sent in their questions. Thanks so much for tuning in. Go to our website, mlsys.stanford.edu, and sign up to our mailing list. Subscribe to our YouTube channel, and next week we're going to have Rudhaja talking about decentralized neural sort systems. Thank you. Bye.